Hi, my name is Nick Carter, and I'm presenting on perceptual filling in from chapters 5 and 6 of Ramachandran's text, Phantoms in the Brain. So what exactly is perceptual filling in? Perceptual filling in is essentially your brain extrapolating information, making inference from information, making assumptions about information that is incomplete in the visual field in order to make it whole and coherent. So most of the time, perceptual filling in, we don't even notice. It's completely outside of our awareness, kind of suggesting that it happens really early on in our visual experience. It happens early on in the brain, so like V1, V2, or V3. And I kind of want to start off by asking a question that Ramachandran asked himself. How sophisticated is the process that the visual system uses to insert information? And to answer this, a lot of researchers have already done a lot of research regarding this and have a wide array of experiments using tricks of the eye. They've asked questions like, what are some of the neural correlates of filling in? What part of the brain is active? They also ask, what are the mechanisms of filling in? Such as, does the brain simply ignore the lack of information, or is it an active process of construction of an image? So a few examples of perceptual filling in. One's called the Troxler effect. Participants look at a single dot, they fixate on it, and there's a halo around it. And then eventually, after a couple seconds, the halo will kind of evaporate and be filled in by the background, the primary color. This also happens with textures and artificial scotomas. And then the area where I'm going to talk about the most is around the blind spot in all of our eyes. So what are the neural correlates of perceptual filling in? Generally speaking, it's well understood that perceptual filling in happens in early visual and extrastriate regions. So is this an active process that these regions are doing, or is it really a passive process of ignoring and just cutting out information? A lot of research shows that it's an active process. One such line of research shows that, or they used a variation of the waterfall illusion, which is a motion adaptation illusion, and they placed this over the blind spot and then had participants fixate while they did this. And then once the stimuli was removed, they still perceived motion there, even though it was all filled in motion. This indicates that filling in of motion and real motion utilize some of the same mechanisms. And motion requires active processing, so moment by moment by moment dealio. And so this kind of elucidates one of the neural correlates. Other experiments have shown that color areas activate. Other research shows that early processing of false contours and such. So what are the mechanisms of filling in, though? Some research has used single cell recordings to look at single neurons that are corresponding from the blind spot to the retinotopic map of V1 and looking at their response to stimuli. Presumably there would be no response in this area, but there are neurons associated with it. So in one test, researchers put progressively larger bars in the person's blind spot in their visual field, and they found that as the bar got longer, there was a stronger response, but it wasn't until the bar crossed the blind spot entirely until this participant perceived it, and there was the maximal response. And this research also showed that the receptive fields of these neurons were relatively large given the rest of the neurons in the V1, which have relatively small receptive fields. So one possible mechanism that has been proposed is through isomorphic theory, and this theory essentially states that there are overlapping receptive fields all the way through our visual field, represented on our V1. And so what are the mechanisms for perceptual filling in? Well, most of the mechanisms are still theoretical, and they're not quite sure why it occurs. There are a couple mechanisms. I'm going to talk about one. It's called scale-selective mechanism for deep layers. So according to this theory, when a stimulus was presented around a blind spot with the end goal of filling in mind, there's activation in the corresponding V1 blind spot region. All of these neurons around the blind spot seem to have relatively large receptive fields, which extend beyond the blind spot region, but they also extend into the blind spot a fair amount. So some of these neurons, they have large round receptive fields that extend a lot of the way into V1, but then there's also other stimuli that have receptive fields for long, elongated types of stimuli, like a bar. And so all of these neurons were found in deeper layers of the columns of V1, and they're selectively active. So when a bar is presented, and it's only presented part of the way in, it will give some response. However, it won't be enough response to say, hey, there's a bar in this right now, we should complete this. It's not until the bar is on both sides that it becomes apparent. So really, why is perceptual completion important? It keeps the world coherent. It keeps it so we don't have big black spots in our visual field. It also gives us a reference for how the rest of the visual system works, and to be honest, it kind of is fun just to stare at illusions and kind of reflect on how they're working in our brains. So I hope you enjoyed this, and yeah.